Hello, everybody. This project, Science on the Bar, is very welcome, and we started such a thing in Israel about 12 years ago, and we used to do it. It started by Weizmann Institute in Israel, and we used to do it that in one night every year. It's still going on. 50 bars in Tel Aviv are open, and each one hosts about 100 to 150 people, and they do it simultaneously, and it was a big success. And I was fortunate to be also lecturing the first Science on Bar in Israel about 12 years ago. And actually, 2 years after I started, something big happened in my in my scientific life. I'm sorry if people don't see me here anyway. And it was the discovery of the God particle, the Higgs boson, and that's what I want to tell you about. So let me first give you a little brief of my life as a Higgs hunter. Higgs hunter is what we call, it's okay, well, shall I stand? I want people to see me. Yeah, okay, here it's okay? For the camera, it's okay here? So actually I was a student, started to be a student in 1987, and Higgs hunters are the name we called for people who were hunting for a particle that we were not even sure that exists. The Higgs boson is a particle that is very important. And I explain today even why it was called the God particle, and I was looking for it for many, many years. And I was a Higgs hunter from 1987 to 2011. In 2011, I got a call which was a life changer for me, and actually the call suggested that I will lead the Higgs group of the Atlas experiment, and I took it upon myself, and I was for 2 years the leader of the Atlas Higgs group, and I was fortunate, very fortunate, that it happened exactly at the time, a year after I was appointed, they discovered the Higgs boson, and it was under my leadership of the Higgs group, and that was a great thing. One of my first students is sitting here, that's Lisa Zivkovic from Belgrade. She is the head of the Laboratory for Energy Physics here at Belgrade, so let's applaud her. Thank you. So, you know, whenever I give the lecture, I used to give many, many lectures about the Higgs boson, and I always get the question, even though I give this introduction, they still ask me at the end. So why was it worth to spend billions of dollars to discover the Higgs boson? Why is it important? What do we get out of it? What can we do with it? What application can we do with it? And I explain to people, I just don't care. We didn't do it for money. We didn't do it as an application. We do science because we do it because we are interested in it. This is all science driven by curiosity. And actually, the story of the discovery of the Higgs boson is a story of curiosity-driven science, or what is called basic science. And countries forget usually to put money in it. It's more important to put money in basic science than in kind of applications and things like that, because if you don't have basic science, the applications will be over and you won't be able to do a thing anymore. So curiosity-driven science is what advances knowledge, and the only thing that competes with curiosity is imagination. You know, Einstein used to say that imagination is more important than knowledge. And his most famous thing that Einstein achieved, one of the most famous formulas in history is the equivalence of energy in mass, E equals mc squared. So if you want to remember the formula E equals mc squared, I know many people know this formula, that they have no idea what it stands for, but they know E equals mc squared. And I have my own initiative for this formula. It says E equals mind times curiosity squared, and that's the way to remember the formula of Einstein. Anyway, let me explain to you why it's important to do basic science rather than applied science. If you do applied science, if we did only applied science without any theoretical and basic science, we would still use chariots or horses to go on the streets. Now, thanks to basic science, electricity was invented and all these things, and now we have missiles and airplanes and things like that. Same thing goes that with applied science only, we would still light candles with nitrogen or things like that. But now we can actually have, thanks to basic science, the www and the internet. You have the internet thanks to basic science. When people started to do communications and computer, they had no idea that they want to invent the internet. It just came. Nobody intended to invent the internet. And by the way, the internet came to the world because of the search for the God particle, for the Higgs boson. Because in around 2000 or something like that, a little bit before, 1980 something, 1990, they were thinking at the laboratory for physics at CERN in Europe. They were thinking, how can we actually, if you have a paper and 1,000 people signed on it, and each one wants to read it just one day before he signs it to make sure that he's part of this paper, it would take 3 years to read a paper. So you need to distribute it all over to 1,000 people at once, and they were thinking how to do it, and that's how the internet was born at CERN, at this laboratory where the Higgs boson was discovered around 1990. So today is the birthday of Tesla, and I give lectures about Tesla. I think he was a real great scientist. He was one of the biggest examples that I have for what is called curiosity-driven science. Tesla didn't care about the money, nothing at all. He didn't care about money, and he was cheated all the time. People stole money based on his genius. But he was driven by curiosity, and his curiosity came from his knowledge in poetry, in Faust of Goethe, etc., and he wanted to understand how the world works. And if you understand the harmony of the world and how the world works, you can do things. And that's how he invented the AC power engine, and he understood the way that you can actually rotate wheels by engine using AC. And that was his genius. And Tesla is an example for curiosity-driven science. If we go now to 1895, this is Thomson. He discovered the electron in 1895. This discovery of the electron by Thomson was purely curiosity-driven science. Everybody asked him, who cares? Who cares? Why do you need to discover a particle that nobody can see? I mean, you breathe oxygen now, you don't see it, right? Why do you care what is the oxygen made of? Why do you care what is the electron? And then the story goes that when they discovered the electron, Tesla took a glass of champagne, like this one here, and he raised it and says to his colleagues that criticize him all the time, to the useless electron. And he took just a few years after Tesla's discovery that real electricity came to the world, and you know, history said everything about it. So that's curiosity-driven science. Tesla did everything that he did with a $100 tube. The one that we used to use in the old television sets, for many people who know, the huge televisions. You can buy today for $100. And at that time, I mean 120 years ago, you could actually do things with laboratories which have only one person and a simple instrument that costs $100. These days it doesn't work anymore, not only in physics, also in biology, in astrophysics. You need the collective genius. You need thousands, hundreds, at least hundreds of people that actually bring themselves together and do science. So if it was possible to discover the electron for $100 with one person, to discover the God particle, the Higgs boson, you need $6 billion, and you need collaboration. And that's how big science was born, with all these laboratories. So the discovery of the God particle is actually the work of the collective genius of thousands of people, and it's what we call big science. And I came from a collaboration called Atlas, but there were two collaborations that discovered the Higgs boson. One was called Atlas, the other was called CMS. They actually were competing each other. So, you know, half of the world joined together forces to join one of these experiments, in this case the Atlas experiment. And this is just part of the Atlas collaboration, part of the people who share the discovery of the Higgs boson. So this is the way they do science, the gene project today. Think about the corona. It was not one person. The whole world was working to find the right immune system, and this is the way. So let's talk about the important things that curiosity asks itself. Curiosity asks itself, what is the world made of? Now we have the answer. We know the world is made of matter, and matter means the atoms, and atoms means the nucleus, which is made of protons and neutrons, which are made of quarks. That's what we know today. And the electrons and the sort of electrons, and then there are the force particles, and it doesn't matter. Another important question is, why do we exist? I'm sure each one of you asks himself one stage of his life, why do we exist? Or how did it all begin? This is a question we ask all the time. That's why some people believe in God, some people invented God, and whatever. But how did it all begin? We really want to understand how did it all begin. And also, what should bother us is what is the fate of the universe. We know, for example, the sun will actually turn itself down in a few billion of years. Don't worry, I mean, you won't be here, neither your grandchildren will be here. It's a few billion years. But then what will happen to the whole universe if we look in the long run? Now, it turns out that the answers to all these questions lies in mass. Mass, you know, the weight, your weight, 70 kilograms, 60 kilograms, 80 kilograms, it all lies in mass. Now, 1964 is a very important year because the Beatles invaded America and the rest is history. But 1964 is also the year that the riddle of mass was solved. It was not yet solved because there was a proposal by Peter Higgs from the University of Edinburgh and another couple of guys, Broughton and Glare from Belgium, from Brussels, who proposed a mechanism to give mass to particles. And their idea was actually that we live and there is a field here. You don't see it. I told you before, you breathe oxygen, you don't see it. You just know that it's there. So besides oxygen, there is another thing here, which is called the Higgs field. And this Higgs field interacts with matter particles and gives them their mass. That was the idea, and I'll talk about it a few more times. But in order to explain what is the Higgs field, I need to explain to you what is the meaning of a field that surrounds you. So the sea level is kind of a field because it's everywhere and it's the same unless you disturb it. And in the place where you disturb it, you can actually surf. And this is what we call a particle. A particle is a disturbance in the field. The field is everywhere. And when the disturbance is moving, you can surface on it, and actually you can surf on it and get from one place to another. This is called the movement or radiation of a particle, like radiation of a photon. So when you use your telephone, I don't have my telephone with me here, but when you use telephone, you call somebody, there is an electromagnetic field here, you don't see it, and the transmission of the waves occurs quantum mechanically, the way we speak it, by the movement of photons at the speed of light. Photons is a disturbance of the electromagnetic field. Maybe you don't understand a word I'm saying, but you know, everybody knows what is the cell phone, and everybody knows that you can do things here that happen there. And everybody should ask himself, how do I do things here and they happen there? Because there is an electromagnetic field all around here, and you create a disturbance in the electromagnetic field. You create photons that transfer your information from here to there, and then you can talk to your colleague, or you transfer information from here to some relayer that sends it back to you, but it's all through electromagnetic fields that go all around here. So as I said, the electromagnetic field is the most famous field. A disturbance in the electromagnetic field is called the photon, and photon is this particle that mediates the electromagnetic force. You know, when you are in high school, you learn that there is an electric force between an electron and an electron. Today we know that this electromagnetic force between electron and electron is actually mediated by force carrier, which is called the photon, the same photon of the light that you're using. Now these photons that mediate the electromagnetic force, they are massless, they don't have mass. Because these photons have no mass, the range of the electromagnetic force is infinite. If you make some source of light here, like a lighter here, the light will go to infinite. It will become weaker and weaker because it spreads on more area. But it will go forever. It will go to an infinite range. Just like the light of the sun is very far from us, very far. But still, the light gets here. It gets here. It's very, very weak when it gets here, but it's enough to warm Earth and give us life. So photons are massless, and as a result of it, the electromagnetic force is an infinite range. But there's another thing that why photons are massless, and actually everything, when it's born, when the universe was created, everything was massless. Because one of the beauties of this universe, and that's also Tesla was talking about it, is symmetry. The symmetry all around us. And this symmetry is something that actually preserves us. And in order to preserve the symmetry, all particles must be massless. But here's a problem. There is another force in nature. Actually, there are a few more forces in nature. There's the nuclear force, which I'm not going to talk about, just a little bit. There's the electromagnetic force, which I talked about already. And there is also the gravity, which I'm not talking about at all. And the fourth and last force is what's called radioactive force. Some people call it the weak force. The radioactive force is actually very short range. If it wouldn't be short range, we wouldn't be here because we would all have cancer. But it's very, very short range. Now, a force that is short range cannot be mediated by massless photons, because if massless photons would mediate it, then its range would be infinite. So the particles that actually take with them and transmit the radioactive force must be massive, very massive. We call them W and Z. And the question was, in around 1964, was how do the W and Z get their mass? How come the radioactive force have a very, 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 very short range? How come it has short range? We have to understand. So actually the questions were very important. How do photons and particles, matter particles, get their mass? Nobody knew the answer. And you can tell me, why is that so important? How do they get their mass? Why is it important? So let's see why it's important. Does anybody here have an idea what is the size of an atom? Let's look at the word size here. Okay, there is a dot at the top of the eye. Now imagine this size is printed on a paper. It's very, very small. Do you know how many atoms this dot contains? How many? Thousands. Well, it's not thousands, it's 7 trillion atoms. 7 million atoms. And you might say, who cares? Who cares? It could be thousands. Would it make a difference? Thousands. Thousands, we wouldn't be here. Let me tell you this. We wouldn't be here, and I'll explain why. And it's actually, the size of the atom is determined by something called quantum mechanics. Okay, maybe you all heard about the term quantum mechanics, but there is something in quantum mechanics that tell you that nothing is certain. There's the uncertainty principle, and it determines the size of the atom. It means that as things are more massive, they are more localized. I mean, you see me very well, and you see yourself very well, and everything here is very, very well localized because it's very, very heavy. In atomic numbers, it's huge. It's an infinite number, weight, okay? When something is very heavy, it's very well localized. Quantum mechanics tell us as the mass is decreased and decreased and decreased, when it gets to zero mass, you lose completely the certainty. You don't know where it is. So the size of the mass of the electron determines the size of the atom. The proton is like the sun of the atom. There is the sun, and the electron is like a star that moves, planet that moves around it. And the nucleus is a few thousand times heavier than the electron. So the only thing that matters for the size of the atom is the mass of the electron. Now, the following thing is happening. If the atom would have been smaller, atom smaller means if the electrons, first I start with the, this is, if the mass of the electron would have been smaller, then the uncertainty in the size of the atom would have been bigger, and the atoms were huge. If the mass of the electron was smaller, atoms were huge. If atoms are huge, they are very far from each other. Then they don't have electric force between them. It's not strong enough. And they wouldn't stay together, chemistry wouldn't hold, and we wouldn't be here. So now you see, if electron would have been lighter, we wouldn't be here. And if you go the other way around, if electron would have been much, much heavier, then atom would have been much, much smaller, and then they were very close to each other, and there would be a competition between the nuclear force, between the nucleus of one atom and another, and the electric force. And then galaxies would not have been formed. Without galaxies, we wouldn't be here. So it's just a miraculous, it's just a miracle, and we can talk hours of this miracle and some other miracles in nature, that electron, exactly this mass that is needed for our existence, if it would have been a little bit heavier or a little bit lighter, we wouldn't be here, and we wouldn't ask these questions. So, let's summarize the importance of mass. No mass, no galaxies, no Earth, no man, nothing. And then we wouldn't have to give answers because nobody would have asked questions, right? But we are here particles do have mass, and we ask this question. We ask, where does the mass come from? And until a few years ago, the only logical answer would have been, since we don't know the answer, God. But the situation in 1964 was that we didn't know how do the radioactive force have short range, because the carriers of the radioactive force must be heavier, and we didn't know how do they get mass, and we didn't know how do electrons and matter particles have exactly the mass that needed for our existence. There was no real scientific answer to this. Until came the papers of Higgs and Gler and Brout, which actually explained the following. There is a field here. The field interacts with elementary particles. I'm talking about the electron, not us, with the atoms inside our body, with the electrons that surround the nucleus, in the atoms, in the zillions of atoms that are making our body. It's like an infinite number of atoms that make each other of us, and the chair and everything else. So the mass of the fundamental particles that is given by the Higgs field is responsible for our past. It turns out that this mass is also, this Higgs field also gives itself a mass. The Higgs field itself, the Higgs particle that is made out of the Higgs field, the disturbance of the Higgs field, which is the Higgs particle, is massive, and that determines the fate of the universe. Where does the universe go to? So one cannot overestimate the importance of the mechanism that gives mass, and this comes by the Higgs. Many, many years have passed since 1964 to 2012, almost 50 years. Until July 2012, we knew there is something called the Standard Model. We made a huge progress. We knew already there's something called the Standard Model, which means that we are made of very few particles, of quarks that make the protons and neutrons, of electrons that make the atoms, and of the force carriers, like the photon and the massive photons that make the radioactive force. But we had no idea how mass is coming. So to explain to you in a more simple way, this was a puzzle. The puzzle was that there was one thing missing, the one thing that gives mass to all particles in the universe. So imagine this girl is a little bit angry because her mother bought her a puzzle, and the puzzle says the Standard Model, and she went to a room and she tries to make the puzzle and it doesn't work. There's something missing, and she goes to the mother and she cries out, "You bought me something bad because there's a missing piece here." And the mother tells her, "No, that's impossible. They never write. You always buy, and there's always all the pieces of the puzzle, and suddenly a piece is missing. Where is this missing piece?" So the mother comes to the room, she tries to make the puzzle, and it doesn't work. A piece is missing. So he said, "Okay, let's call the manufacturer and ask the manufacturer to send us the missing piece." She goes to the box, and she sees the Standard Model made by God about 14 billion years ago. So you cannot call God 14 billion years ago. So how would you get this missing piece? So there's only one way to get the missing piece. Take special scissors that can actually cut in this puzzle of the world from 14 billion years ago and make this missing piece. And this is exactly what we do with particle accelerator. We actually use a technique that actually takes us back 14 billion years ago to the energies, to the density of energies that existed 14 billion years ago, and we collide protons with protons, we smash them in order to produce this missing piece, the Higgs particle. This Higgs particle is produced in about every 15 minutes of collisions, and we collide 1 billion protons with 1 billion protons every second, 1 billion with 1 billion every second. That's what we do in Geneva. So as I already explained to you, the way to make a particle out of the field is to invest energy. That's E equals mc squared. Once you invest the energy, you can actually create the particle. So we need to invest energy in the collision that is at least as big as the mass of the undiscovered yet, unknown yet Higgs field. So if those who can see the movie, I know that very far it's very difficult. So actually in Geneva, 100 meters below ground, there is a tunnel, 27 kilometers in circumference. And this tunnel, we have something called a particle accelerator, We collide protons, 1 billion protons with 1 billion protons every second. And in order to see what's happening in the collision, we put them a bionic eye. This bionic eye is a detector. This detector actually detects electronic signals from the collision and create a picture. So that's like taking a picture of a collision that took place 14 billion years ago. Now, one of some trillions of collisions, there should be a Higgs boson. And we want to discover it. We want to actually dig the Higgs boson out of this collision if it exists. And that's what we did. Now, this bionic eye detector is as big as a cathedral, okay? This is as big as a cathedral. It's about 50 meters by 20 meters in the diameter of the detector. This is the Atlas detector, as I explained. Its weight is 10,000 tons, okay? So it's not it's something big. That's another picture of this detector. Now, it's all happening in the Southern European Research Nuclear, the European Center for Nuclear Physics, which was actually founded in 1954. The former Yugoslavia was one of the 12 founding member states at CERN in 1954 until it departed in 1961. However, nowadays there are 23 member states. Serbia became the 23rd member, the last one, state of CERN on 24th of March 2019, for your information. This is a picture from 2019, May 2019. You know the left person better than me here, I'm sure. Okay. So the Large Hadron Collider, that's how it's called, because hadron is another name for a proton. The Large Hadron Collider started to collide protons with protons at the speed of light at energies that are similar to the energies existed in the universe 14 billion years ago, around 2009. This is the joy of the people who saw the first collisions of proton. Here is a picture. Here is like a photograph of the bionic eye of a collision of proton with proton. So you see, it's really, really beautiful. I call it semi-animation because it's based on the electronic signals that occur during the collisions. But it's the same thing. What you see, the picture that you see is as good as this picture because the picture that you see is just the reaction of your eye to photons that enter into your eye. So you have an electronic signal in your eye as well. Anyway, so what we discover is not actually the Higgs particle, the Higgs God particle, same thing, not the Higgs particle, but its decay product. The Higgs doesn't live long enough. It immediately, as it's created, it decays into other particles, and this is what we want to discover. There are many possibilities for the Higgs to decay to, and it has different phases. Here are pictures of Higgs bosons. These are the things that we discover. This is a Higgs boson that we discovered via its decay to 2 photons. You see the 2 yellow streams. These are 2 photons that come out of the collision. This is a picture of a Higgs boson decaying to 4 electrons. These are the 2 red and 2 blue lines that you see here are 4 electrons that you see here. This is a picture of a Higgs boson decaying into both what we call muons. Muons are heavier electrons and light electrons, as you know. This is a decay of the Higgs boson to 4 muons. As you can see, it's really beautiful pictures, and this is what we strive. This is what I spent 25 years of my life. This is what we wanted to see, and we were not sure it's there. There was a theory of Mr. Higgs from 1964, 50 years old theory, but nobody managed to see it. People were very frustrated, and we hope that one day we will invest enough energy to produce the Higgs field, because the assumption was all the time that we don't see it because we don't invest enough energy to disturb the Higgs field and create the Higgs. You need to disturb an energy which is at least as strong as the mass of the Higgs. If there's not enough energy, you won't produce it. So every time people simply build bigger accelerators with bigger collision energies, hoping to see the Higgs boson. So how often we produce a Higgs boson? As I explained, once every 15 minutes. It's like a needle in a haystack. So the chances, okay, we have a little bit of rain, but it will go away very, very soon, I hope, because it's... Anyway, so the chances, when you have a collision, to discover a Higgs boson, the chances are 1 in a trillion. It's like I tell you that somewhere in the ground here, there is a specific leaf on the grass which I painted all over the world. Go out and find it.
So your chances are as big as discovering the Higgs boson. So we are playing with very, very, very small numbers. So how do we discover a particle?
So actually, I was exactly at the point, the third part and last part of my lecture, where I wanted to explain to you how do we actually, what practically we do in order to discover a particle. Because there are lots of things that come out of these billions of collisions, and you want to identify those collisions where we see a God particle, which is very, very difficult. So actually, it's a test of two hypotheses that you try to test one against the other. One is that there is a Higgs boson, there is a God particle, and the other that there is not. But it doesn't work. Let's see. Maybe now it will work. Okay. So imagine a jar which has many, 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 many billions of coins, and it has the same amount of coins from each value, from say 0 to 100. It has the same amount of coins. And you start to spill coins out of these jars. So the question is, we know maybe, the hypothesis of the background is there is no special coin here. And the hypothesis of the signal of the Higgs boson, there is one coin which we don't know what is its value, that is in excess. It's like instead of having the same amount as the others, it has many more than the others. This would be the Higgs bosons. So we start to spill coins, and we start to spill, and first we see after we spilled about, I don't know, something like 100,000 coins or something like this, we should get about 10,000 of each value, and we see that we get a little bit more at the value of 125. Now, the probability that it just happened by accident, that there is no special coin, the probability is very, very low. It's about 1 to 1,000. It can happen. It can still happen. It's like tossing a coin for about 10 times and getting head all the times. It can happen, but the probability is very low. If this is the case, this plot here shows you the probability. Around 125, the probability that there is no Higgs boson, is about 1 to 1,000. Would you call it a discovery? Did we discover a new coin, or did we not discover a new coin? It's the point of how much you trust that you are so lucky that by chance you toss the coin 10 times as you get head all the time. So we call it an observation. If that happens, where we should see a new particle, we call it an observation. However, if we keep on tossing coins, here we toss about, I don't know, about more than 1 million coins we toss, and we keep on seeing a special thing happening at 125. Here the probability that it wouldn't be something special would be 1 over 10 million. This time we say, probably there is something special around 125, and we call it a discovery of a new particle. You'll understand me better when I show you the next thing. This is how we discover the Higgs. We discover it by a signal which is Higgs decays into 2 photons, the same photons of light. Now you see very well here that around 125 we see a bump, and the probability for this bump is say 1 to 10,000. We call it 4 sigmas. That's how we call it. And we say, maybe this is it. Maybe this is not just an accidental bump, not an accidental bump, but say the real thing. Maybe it is. So I'm going to tell you the moment when personally I knew that we have a Higgs boson. And I want to quote the words of Barbara Cannon, who was the president of the Royal Swedish Academy of Sciences when they gave the Higgs Nobel Prize. She quoted something for the book of Isaiah, saying, "Those who walk in darkness shall see great lights." And she says, these are the great moments in every scientist's life when he realizes that he can suddenly see something that nobody before him has seen, and a new light is shown in nature. And this is actually what I'm going to tell you now is my personal enlightenment moment. I was in Paris with two of my friends, Marumi Carter and Alex Reed, and it was midnight of some night in November 2011. It was something like the 27th of November 2011. I was already the Higgs leader of Atlas, and we were actually expecting information that came from the laboratory, from CERN. They were looking for the Higgs decaying into two photons, and we were waiting for the information, and it didn't come. And around midnight, Marumi told me, do you want some grappa? It's called Prima Uve. And I said, yes. And he said, no, it's better you don't take it because you'll fall asleep. And I said, no, I wouldn't fall asleep. He gave me the grappa at midnight, and he had to wake me up again at 3 a.m. in the morning. At 3 a.m. in the morning, he wakes me up, he shakes me and says, Eilam, do you want to see the Higgs? I said, what, Higgs, where? And then he showed me this plot. Now, if you understood me, this is exactly the plot that shows you that around 125, we have a fluctuation that is really, really not probable from a normal thing without the Higgs. This must be a new particle. And we knew that maybe we have something really, really particular around 125, the mass. Now, what you see here is actually how we collected data in time. You see, nothing is happening until you spill enough coin, and suddenly you see something happens around 125, and this is actually the Higgs boson. This bump around 125 shows you that the data indicates the existence of a new particle, which is the Higgs boson. This is exactly like tossing the jar with the coins. This is I showed you how we discovered the Higgs with the two photons. Now I'll show you how we discovered the Higgs when it leaves very, very small time and then decays to 4 electrons. It's the same thing. Look what happens around 125. You have the arrow that shows you where to look. Look in this area of 125 mass. Look at where the arrow shows you. You see something is building up there. That's the Higgs boson. Without the Higgs boson, we shouldn't get this fluctuation. You see something builds up there. And now we'll extend the region so you can see around 125, we have a Higgs boson. That's how we knew that we discovered a new particle. And what we see is a fluctuation that is not probable. If there is no Higgs, what we see can happen in 1 to 10 millions. So probably we have a new particle. This is called 5 sigma, or 5 standard deviation. So we knew we have a new particle. And then we decided to announce it at the 4th of July 2012. The rumors spread around, and the night before, people gathered near the hall where we should give the lectures. They gathered and were actually accumulated to the stairs, and they slept over the night just so they have the privilege to go into the auditorium and listen to the talk of the two spokespersons of Atlas and CMS announcing the discovery of the Higgs boson. This is Peter Higgs, the man himself, walking into the audience. He was around 83 years old at the time. We knew that if the CERN management invited Mr. Higgs, there's going to be an announcement. And this is Sao Lan Wu on the right, the Chinese woman, talking to Mr. Higgs and telling him, I was looking for you for over 25 years. She started around the same time I started, and he answered her, now you have found me. And this is Mr. Higgs meeting Francois Englert, who shared later a year later, the Nobel Prize with him. And actually, they met for the first time ever. And they were sharing a Nobel Prize later. And this is the moment where the Atlas spokesperson, Fabiola Gianotti, and the CMS spokesperson, Yanni Candela, announced the discovery of the Higgs boson with a 5 standard deviation fluctuation. Now, all those people who waited in the corridor and didn't sleep a whole night, they fell asleep during the seminar. So for those, I would say, those who sleep in darkness should see no great light. They missed the moment I mean, they went into the auditorium, but they didn't manage. Rolf Hoyer, the director of CERN, said, I think we have it. Do you agree? We have a discovery. We should state it. We observed a new particle consistent with the Higgs boson. This is a milestone. Mr. Higgs himself says he was 83. It's really an incredible thing that it happened in my lifetime. He was actually joking about the short lifetime of the Higgs. So it's really an amazing thing that it happened in my lifetime. He's still alive. I mean, we applaud. The media says that the Higgs boson was treated like a rock star. The Atlas Higgs group had a party. And then came the paper. The way that science works is that when you have something to say, you actually write a paper. But this was a very special paper because 3,000 scientists signed on the paper. This is big science. This is the glory of big science. All the 3,000 people from Atlas were signing the paper. There was a similar paper from the other collaboration, CMS, with another 3,000. So altogether, it was 6,000 people discovering the Higgs boson. This has never happened in history before. The 6,000 people shared something that deserves a Nobel Prize, not 1, 2, or 3. So the prizes started to come. The first prize was given to the spokespersons of Atlas and CMS. It's called the Fundamental Physics Prize. It competes with the Nobel Prize. It's not as prestige, but it has much more money. It's about $3 million for the one who gets the prize. It's called the Fundamental Physics Prize. And the two of the spokespersons, one from Atlas, one from CMS, said, this is not my money. This money belongs to 6,000 people, so I cannot use the money. So, for example, Fabiola Gianotti and Peter Jenny from Atlas used the money to establish a Atlas PhD grant, which they give prizes every year. And one of the winners in the CMS, Johnny Candela, actually used the money to establish the first CMS Fundamental Physics Scholarship Prize. Then Fabiola was actually a runner for the Time Woman of the Year. She was the spokesperson of the Atlas collaboration, after which she became, and she is still, the director of the CERN, where we discovered the Higgs laboratory. In 2013, Peter Higgs and François Englert won the Nobel Prize. The third partner, Robert Proud, died the year before. You cannot give a Nobel Prize to people who died, unfortunately. Now, the story goes that when they had to announce the Nobel Prize, it didn't happen in time. People were waiting and the announcement didn't come. And it took an hour too long, and it never happened before. And the story goes that the reason was that there were still arguments in the committee. Maybe they should break the rule that only 3 people can win the Nobel Prize and give the prize for CERN, for the laboratory, or for Atlas and CMS, because they were the discoverers of the particle that was predicted by Higgs and Englert. At the end of the day, they decided that in the prize announcement, they will say that this prize was given due to the fact that Atlas and CMS experiments saw the particle. We were very disappointed, but we were sure that this time the committee will change its rule, because it was not a written rule, it was a tradition. And they will give the prize to the real people who made this thing. It's the Atlas CMS 6,000 physicists, but they didn't. And then Englert gave his speech, and Higgs gave his speech, and believe it or not, both of them are still alive 10 years after. And this picture was taken 2 days ago when they celebrated at CERN, 4th of July. 4th of July was 5 days ago. When was it? 6 days ago, a week ago. They celebrated at CERN the 10 years anniversary for the Higgs boson. And you can see that Englert and Higgs were actually giving the greetings from afar. So I want to end my lecture by explaining why is it called the God particle, okay? So I think that there are 2 reasons. First, a poetic reason. I say I'm inspired by Tesla's interest in poetry. So it's actually a poetic reason. I always thought till 2012 that the reason why the Higgs boson is called the God particle, because without it we wouldn't be existed. So there is a logical reason, poetic reason, to call it the God particle. It plays the role of God. But then in 2012, when the Higgs boson was discovered, Leon Lederman, who was very old, and he wrote a book called The God Particle in the 80s, said that the reason why it was called the God particle is because he wrote a book in 1985, why we search for, since 1964, why we search for a particle which we don't find, and he called it the goddamn particle. And he wanted to call the book the goddamn particle. But the publisher looks at the name and said to him, look, the goddamn particle doesn't sell. Let's call it the God particle. And that's how the name, the God particle, was born. So my conclusion is that we managed to actually establish and actually fulfill the puzzle of the standard model with the Higgs boson, and the puzzle is finally completed. We know now the structure of matter in the universe. We are very happy with that. We actually completed the picture. And in the words of Barbara Cannon, we walked in darkness for 50 years, trying to shed light on another dark page of nature because it was not lit. Now Atlas and CMS illuminated another page in the book of nature for generations to come. 6,000 physicists made a mark on history. Thank you very much for your attention. Thank you. I can take a question or two if you have. Don't be shy, come on. They warn me that the Serbians don't ask questions, but I mean, break the rule, I mean. Okay, thanks again. There's a question here? Go ahead. It's okay.
You said that Higgs boson decay on first time on 2 photons and next time on 4 electrons. And how that can be?
Okay. She says, I said that the Higgs boson decays to 4 photons and then to 4 electrons. How does it happen? Okay. So first of all, it's not for first this and then this. It's probabilistic. Quantum mechanics tells us that nothing in this world is certain. Everything has some probability. There are choices, and nature chooses the possibilities that happen to us. This is the way quantum mechanics works. This is the physics of the very small, the physics of the atom. So what happens is when there is a collision, first of all, there is a very small probability, but sometimes the Higgs boson is created. And then there is a probability for the Higgs to decay to 2 photons, and different probability to decay to 4 electrons. So it's like tossing a coin. Sometimes it's head, sometimes it's tail. Sometimes it decays to 4 photons, sometimes to 2 photons, sometimes to 4 electrons, sometimes to other particles. So, but the Higgs decays because it can do it. It's like a stupid answer, but it happens because it can do it. When I drop, okay, I won't drop, don't worry. When I drop this, it falls down. The reason because it can, because there's a lower energy here and it can fall. Why doesn't it fall to the center of the Earth where the energy will be lower? Because it cannot do it, because something holds it. So the Higgs decays because energy allows him to decay. Everything goes to the lowest possible energetic state in nature, including yourself. Everything goes into the lowest energy. And the decay product of the Higgs is at its lowest energy. It can do it, so it decays.
So it decays only on 2 photons?
Yeah, no. It has about 8 possibilities that it can decay.
That's one possibility. When it decays on 2 photons,
yes.
There is nothing but 2 photons.
Right.
But photons don't have mass, you said.
Right.
And it happens
I want to explain.
Something which is
excellent question.
Mass,
excellent question.
which doesn't.
Excellent. Okay, she asked how can a Higgs decays into 2 photons.
The photons have no mass, but the Higgs have large mass. So how can it decay to? What happens is that the photons do not have mass, that they have energy. And energy is equivalent to mass. So what happens is that the mass of the Higgs actually change itself into energy. And this energy goes into the photons. It's E equals mc squared. It's simply an expression of E equals mc squared. That's what it is.
But can we then express mass only as energy?
She says, can you express mass only as energy? And the answer is absolutely yes.
Why do we need mass?
You ask why do we need mass, but that's the point. That's the big discovery of Einstein in 120 years ago, 115 years ago. This mass and energy is equivalent. There's no advantage to mass, no advantage to energy. They actually play within each other. I mean, what is mass for one observer is energy for another observer. It's the same thing. Mass and energy is actually equivalently the same thing. It depends on your point of view. You are welcome. More questions now that we had one? Good, go ahead.
How did the discovery 10 years later?
Can you give, please, an example of some development today, something practical from daily life that changed because of the discovery?
Oh, thank you for this question. Didn't I tell you in the beginning of the lecture that no matter that in my introduction I said that I don't care about these things because I do basic science and I don't care what can be done with it. Somebody will ask about what did you do with it, and it came. And so the truth is that it takes more than 10 years for things to happen. Until applications come from basic science, it takes much more than 10 years. I mean, it took at least 30 years since the discovery of the electron until we knew how to do things with it. So I believe that something will come out of the Higgs discovery, but the important thing I want to say, that in order, and I said it in the interview to the television in the break, that because of the work that we are doing at CERN, we had to develop things which are state-of-the-art. So using collisions, we had to develop, first of all, imaging devices and actually guns that shoot particles. These guns are used to cure cancer, and the imaging devices are used to identify the cancer or trace the cure of the cancer. So medical physics is actually a result of all this basic science. Even though we don't have direct consequences in physics, we have consequences to other fields. Think about your telephone. All these things happen because in order to do basic science, you have to do state-of-the-art technology. And with the state-of-the-art technology, you take it to all other things that you're asking about. Okay? That's the best answer I can give. Yes. Oh, wow, it started. Great. Yeah. Can I have the microphone here?
What is the next big discovery?
Okay, the question about what is the next big discovery, that I can answer, but then you ask what is the next thing that is going to happen at CERN. That I cannot answer. I believe the next big discovery will be dark matter. You know that I know that you know, but only 5% of the universe is visible, and 95% is dark energy in dark matter, and there is a race now to discover dark matter, and I have a belief, and it's not good for a scientist to believe, because scientists should not believe, but I have a belief that the next thing that is going to happen, that we will understand finally the nature of dark matter, and we will discover it. Now, about CERN, there is a little bit of a problem now that in order, from the day that you decide that you want a new accelerator and increase your energy to discover new particles, it takes 10 to 20, 30 years till you build it, okay? CERN has not started to do any new thing yet. So the current accelerator will run with more collisions, what is called high luminosity. And hopefully we will manage to discover the way that Higgs gives mass to itself and explain the fate of the universe, the stability of the universe. That is the only thing that I can expect from CERN in the coming years, because I don't believe that other new physics like something called supersymmetry will be there. But you have to invest money, you have to build new accelerators, and then you might find new particles, and then you will advance technology, and who knows what will come out of it, as I explained before. More? Wow, look, the Sapiens do ask questions. Who said that they don't? Yeah.
Okay. So my question is, like, okay, at some point you were doing all these experiments and you were getting in results, and at some point after years and years of research, you got a 5 sigma result. My question is, was that enough for you? Were you at any point like, okay, we got a result and we have it being statistically significant, but like 5 sigma is a consensus. 5 sigma is just something that we kind of agreed on. So were you at any point like, okay, maybe we're just reading into it. Maybe we're just trying to find the Higgs boson. Maybe it's not there, but we have this data. We're thinking that it is, but maybe we're wrong.
Okay. So first of all, by the way that you asked the question, I see that you do science in some way. I don't know how. Because 5 sigma, okay, so first of all, we stopped looking at 9 sigma. Okay, we stopped looking at 9 sigma. Your question is good because you're not certain of anything in this world. Maybe it's not a Higgs, but after 9 sigma, we decided to stop. But personally, me, myself, after the discovery, I stopped doing these things and I moved into machine learning and artificial intelligence. Because I thought that there's nothing more for me, and I decided to switch fields, and I think this is going to be the next big thing. Something to do with artificial intelligence is changing the world now, completely. We are in a revolution. People don't know it, but we are inside the revolution now, the revolution of artificial intelligence. It's happening right now at this moment. Any more? Yes. Wait, microphone. There.
So you mentioned that when it decays to electrons, it's usually 2 or 4. Is the reason known why they always come in pairs?
You ask if why electron comes in pairs? Yes, there is a reason. It's a very intelligent, thank you for the question, very intelligent one. The reason is that the Higgs doesn't really decay to electrons. They are very light, and it doesn't care about the electrons, but it decays to these Z particles I was talking about, the force carrier of the radioactive force. And this Z decays into electrons. So when a Z decays, it decays always to a pair of electrons, 1 electron and 1 anti-electron, because the charge has to be conserved. So electron has a negative electric charge, and the anti-electron, the positron, has a positive electron charge. So that's why it comes with always in pairs of E plus, E minus. The Higgs is natural, is not charged. Neutral charge, 0 charge. So it cannot decay to a charged particle. Always a pair. One has to be charged positive, one has to be charged negative. Thank you for the question. Any more questions? Okay, looks like this is it. Thank you very much. Thank you.